Today we're talking about geologic time and Earth history, thinking about relative time dating and absolute time dating. You maybe have done something similar to this in maybe kindergarten or elementary school, where you saw something like this, where you were asked to put these events in order based on what you know about each one. Now these people are clearly baking a cake. Knowing what you know about that topic, you would probably decide that the picture here in the middle is step number 1. Over here, putting the cake into the oven would be step number 2. And the third and final step here would be this guy enjoying the cake. Now again, this is something we know because we've seen somebody, or eaten a cake before, right? So these are kind of common sense rules we have for cake making. When you look at something like this, the Grand Canyon, you probably don't think of all kinds of common sense rock rules, but that's where we're going to get today. We want to know the rules that we need to be able to put rock events in order. So that's our focus for the day. Before we get to those rules, let's really talk about what is relative time. Okay? Relative time is determining order of rock layers and figuring out how they were deposited using no dates. Only using what we know about the event, just like we did for the cake. We didn't have a time that we had to figure out when the cake was being made. All we had was what we knew about cake making. Same kind of thing here. When we put the rock layers in order, we aren't going to have any dates involved. Just common sense rules about how rock layers form. Now this is my relative timeline. Things that have happened in my life. I don't remember a date for all these things, but family vacations, my sister, graduating college, getting married, getting a job. Based on what I know about that memory, I can put them in order. I know our first vacation, I remember, was just me and my parents. My sister wasn't around, so I would know her birth had to come sometime after that family vacation. Right? I don't remember the exact day I graduated college, but it was before I got my teaching job and made a lot of money. So again, I don't have any dates, but just what I know about the event clues me in to the order relatively. Okay? When we talk then about absolute time, what we're doing is putting things in order, like rock layers, or events like faults or volcanic eruptions, layers or events using actual dates. Okay, here with absolute time, I have the actual date, so I've got my calendar here to kind of show that. Okay, actual dates are used in absolute time. So that would be like in my cake example, if there was a little clock in the background saying, oh, this is what time it is for each one of these examples, and then we could put it together by the timing of the event. That would be absolute time. So let's go through our common sense layers of how rocks form. Okay? These are fancy named rules for pretty simple layers. This first one is called the principle of original horizontality, and I want you to look at the root there, horizontality. Okay? Horizontal. That means flat, right? So that tells me that layers must be horizontal when they formed originally. Okay, when originally deposited. And I like to call this rule the rule of the cake layers. That's kind of my common sense name for it, right? A cake has to start out with flat layers. They have those TV shows where they make crazy fancy cakes, but they have to start out horizontal. So in that box there on the side, just draw a little example kind of like these. You can split it in half and do like a before and after picture. On the left, let's do a before, showing that they started out horizontal. And on the right, we can do an after, showing they got tilted sometime later. Again, the rule says they have to start horizontally. They can change after the fact, but they have to start out horizontally. Rule number 2 is the law of superposition. Okay, saying that in an undisturbed sequence of rocks, I typically see the bottom layers as being the oldest, while the top layer is the youngest. And this I call the rule of dirty laundry. Okay, this rule tells me kind of common sense, like my laundry basket. The oldest layers are on the bottom and the youngest are on the top, right? The outfit I wore the longest ago, I can find near the bottom, where the most recent one I found on the top. So in your box there, make some nice horizontal layers. And we're simply going to label down here at the bottom, this is my old. And at the top, this is my young. Okay? If I were going to number these, just like I did with the cake example, I'd start out with a 1 on the bottom, 2 for the next layer, 3, and I'd end with the youngest being the final step, number 4. Now, not all rock layers look perfect like this. This is a spot in the Badlands where we can see the nice horizontal layers, okay? Knowing the oldest is at the bottom, youngest is at the top, but they don't always look perfect like this. Here's an example of something that we call folding, where we can see the layers are no longer horizontal, but they have this curved shape to them. So at the very bottom, we have this chart. We want to fill it in, okay? This is called folding. And folding occurs, what does it form from? It forms from something called compression. And compression would happen when the Earth is moving towards each other. So of course we would say that that could be a convergent boundary. Compression. Right, so this happens when the Earth or the plates are moving towards each other. The layers start to fold and we see this kind of wavy pattern happening within the rock layers. Now when you see this on a cross section, you would then fill in, well, what layers are being affected. And here I might say layers 1, 2, 3. Okay, this is another example I can see of a change in rock layers. This would be a fault. Okay, here I have a crack in the Earth's surface. There's the crack. And I know this is a fault because I can see this layer has shifted down, so this layer no longer matches up perfectly. This is a fault. That's the next picture in my table here. So what is this? This is faulting. Okay, and this is formed from pressure. And again, that can really be from any type of plate boundary. We talked about faulting mostly with transform, but it can really occur anywhere. The final deformation we can see is this. Okay, we still see the layers pretty consistent with each other. However, they are now no longer perfectly horizontal. We call these tilted, right? Even though they're still stacked nicely one on top of each other, they're at an angle. So the last one on our chart here, we call this tilting. And this we say happens really from any kind of movement on the surface. That's not working out. That one would be movement on the surface. Okay, looking then at my next two rules, principle of cross-cutting. This is a feature when I have something like a fault, a crack, or an intrusion of magma, And that fault or intrusion has to be, looking at how it comes into the cross section, it has to be younger than the rock layers it cuts into. Now I call this rule the rule of photobomb. Okay, because what's happening here is these two layers already exist, right? These two layers existed when this igneous intrusion decided to pop in. So this guy is my photobomber. These guys are the people taking the picture. They had to exist first before this next layer came in. So go ahead and get that drawn in on your notes page, right? In that empty box. Put in a couple layers. Draw in that layer coming from the bottom. And if I were to number these, I'd know I'd have to start out with the bottom layer as my 1, second layer right above it, and this would have to be layer number 3. Okay, this had to exist after these layers came in. I know though it had to be before these guys because there's not cutting into them. So this would be my number 4, and this would be my number 5. My final rule then is going to be my principle of inclusions. This is what you want to copy into the box there. Go ahead and draw in a couple layers. The main thing we're looking at here are these rocks inside, what is included inside the rock layer. So make sure you get those apparent. And we like to call this the rule of chocolate chips. Okay, thinking of these as chocolate chips, I know that these have to exist first before the layer around them. So when we talk about this rule, we say that a rock layer with inclusions or pieces of other rock, holy moly. A rock layer with inclusions must be newer or younger than the actual rock pieces. They already had to exist before they got put in these rocks. So the pieces are older than the rock layer that they sit in. This would then be younger. Okay. Our last thing to talk about then is unconformities. Okay, what is happening in an unconformity is we see it is a gap in the rock record. Part of the rock record is missing due to weathering and erosion. Things like rain, wind, glaciers, gravity, runoff. All those things are coming in and removing parts of existing rock layers. So here I notice a unconformity, okay, an area where this rock layer is not a perfect match to this one. What happened is this layer existed, something came in, runoff, removed the top part of that layer, and then this new part was shown on top. Looking for that dark wavy line, that would prove to me an unconformity is present. There are 3 types of unconformity. The first one here is called a disconformity. This is when I have an unconformity between 2 of the same rock type. Okay? This is when I have a gap between 2 layers of rock that are both sedimentary. Okay, so 2 sedimentary layers of rock on either side of my erosional line. And they don't have to be exactly the same. Okay, it can be between a sandstone and a limestone, or a limestone and a shale, but they do have to both fall in that sedimentary category. Now here I have 4 existing layers of rock. What I notice is that the erosion comes in, removes part of the layer. Over time, as those new layers start to build up on top, this place where the erosional contact is, this becomes my unconformity. This line here is my unconformity line, and because I have sedimentary underneath and sedimentary on top, I would classify this as a disconformity. Here's an example of what it might look like as we work through our practice problems. The second type of unconformity, this is called a nonconformity, and I always think about the phrase not the same rock when I think about a nonconformity. I still am seeing a gap between 2 layers, but now those 2 layers, the lower one is igneous. So I have a granite or basalt underneath. This has to be my igneous rock. And then once the erosion comes in, I end up with a sedimentary rock on top. So again, special effects, erosion comes in, removes part of the layer, then over time the new sediment piles in on top, showing the unconformity here as the dark wavy line. Again, because igneous on the bottom, sedimentary on top, this is classified as a nonconformity. The third and final type of unconformity is probably the easiest one to recognize. This is an angular unconformity. And we call it that because look at what's happening down here at the bottom. These layers underneath are tilted. The rock type is not important. Okay? What's important here is what's happening to the layers underneath. So I'm talking about the layers on the bottom have been angled or tilted. And above those tilted layers, what I have is horizontal layers on top. So because of the angle here and the flat on top, I've got my unconformity. And this one typically doesn't show up as wavy, but simply because of the angle on top and the horizontal above, that stands out pretty good. At the very bottom of your packet there, you have a chart to help you write the history for these events. Okay? When you see one of those erosional lines in the packet, you will use this chart left to right, starting out with weathering and erosion of the layers that are affected creates, and then you're going to say, what type of unconformity would this be? Now there may be times where you plug in this for the end, uneven earth surface. If it's an unconformity with the sky on top, you would then end with that category, okay, uneven earth surface. So again, these are just some common sense rules for both layers and events to help us piece together how to date relative time rock cross sections.